Just a quick note on posted announcements. Your final homework is now posted. Okay, homework number 13 and MATLAB homework number 13. These are not due until 1 week from Friday, all right, because obviously this Friday is the day after Thanksgiving. Okay, and so really, I mean, this will have applications of differential equations across all the different types of things we'll talk about even next week. However, the recipe for how to solve a differential equation, you guys already know what it is. We did some first order differential equations last time, kind of set up the spring mass vibrating system. We're going to do that today. So really, by the end of today's lecture, you will have what you need to be completing that homework. Okay, and then I believe you guys also all got an email from Josh about the MATLAB final. Okay, so beware again that the MATLAB final is coming up, that the review sessions are out there, and that's going to happen during the last week of classes, regular lab meeting. Yes?
The MATLAB final takes place in a 2-hour session, right?
I don't believe so. I believe it is, look at the details in the email, but I think the way they're doing it is 11 people at a time, right? And you do half of your lab, and then you do the second half of your lab. If you have a question about the administration of that, send an email to your lab TA. Okay, the lab TA is running the MATLAB final. Okay, does what I just said consistent with what your TA told you? Yes? So, I mean, the thing is, there's only 11 lab stations, right? 22 people in a lab, and so you don't have a partner for the final. So I believe they've got it broken up by like half the class list is the first hour and the other half of the class list is the second hour, and that's how we're doing it. But it occurs during your regularly scheduled lab period, okay, whether you're the first or second half. Other questions about that? Okay, very good. So otherwise, I talked about the old final exam solutions last time. So we've got the 3 finals up. You guys can start prepping over Thanksgiving break if you want to do that. We're in really good shape, right? Because it's a full 2 weeks from Thursday before the final exam. Okay, so you got the whole last week of classes, and then finals week, Monday, Tuesday, Wednesday, exam is on Thursday. Okay, so with that, we will continue on with differential equations in mechanical systems. So last time where we left off, okay, we were talking about the spring mass system, and I brought some springs and masses again so we can kind of remind ourselves. Okay, but you know, here's where I think we were. Okay, we had a physical system that looked like a spring and a mass. Okay, so the mass is hanging from the spring. So here's the M, and I've got a spring constant over here, K. Okay, and the idea is from the equilibrium position, we were going to measure the oscillation of this guy, y, as a function of time. Okay, and the equation that we came up with was a second order differential equation that looked like this. It was m times y double dot, right? The two dots is 2 derivatives, plus k times y of t, okay, was equal to 0. Okay, and then we're going to need on top of this plus some initial conditions. Okay, and we'll talk about what those might be for a free vibrating mass. Okay, and so, you know, I think the question we wanted to ask, and this was part of the focus of your lab as well, but we did an experiment in here that was a little counterintuitive, right? And basically we looked at the oscillation of one mass, and we realized that if we put a second mass on there, okay, then a couple things happen. Number one, a second mass will stretch the spring out, right, twice as much as it's stretched out. So here's the undeformed. Here it is, you know, here it is with one mass. And so we put the second one on. Okay, and what ends up happening is now the thing is stretched twice as long. In a static situation, Okay, but then we actually looked at the oscillation and realized, yeah, it also goes slower. Okay, and the hypothesis was, well, it probably goes twice as slow, right, or half as fast. 6 of one, half dozen the other. Okay, and then we realized by experiment that that's not the case, right? And so how much slower did this thing go? Do you guys recall? When I did one mass, in 10 seconds we counted how many cycles? 10 cycles we did, right? 10 cycles in 10 seconds because my spring here is just bent just correctly to give me 1 hertz, right? And then we put 2 masses on and we got how many cycles? 7 cycles, okay? So we got 7 cycles in the same amount of time, and obviously 7 is not half of 10, okay? And so it begs the question of what's going on here? Why doesn't it just scale that way? And I said, well, we're probably going to want to solve a differential equation, okay, to figure that out. So this is the plan. And as I had promised, as we solve these differential equations, we are going to follow the recipe, okay, but I want you guys to really be active in the recipe here to make sure you're all with me, okay, and so help me out. Okay, again, you're permitted to answer only 1 question per class from here on out. What's step 1 in solving a differential equation? Constant coefficients.
Finding the transient solution.
All right, so Ricky said transient solution. Okay, and as part of your answer, why don't you tell me what do I do to find a transient solution?
Set the right-hand side equal to 0.
Okay, so the right-hand side is going to be 0. Now for this problem, do I have to do anything? No, the right-hand side is already 0 for this particular problem. Okay, so that's taken care of. So what's next? Somebody else? Good.
Find the steady state solution.
So am I done with step 1? No? Okay, so what's next on step 1? Do you want to keep going, or do you withdraw your hand raise? Okay, he withdrew. All right, yeah, go ahead.
You plug in e to the st.
E to the st. Why am I substituting e to the st? To get like terms, right? The point is I got to take something, a derivative twice, and no derivative, and still be able to add it up and get 0. Right? We use e to the st because it's the function that will always give me like terms when I take derivatives. Okay, great. So let's go ahead and let, right, y tangent of t be e to the st. Okay, and then plug that in. So if this is true, then what's y double dot? What's the second derivative of e to the st? Yeah, right. The first derivative is s e to the st. The second derivative is going to be s squared e to the st. So these are the 2 things I need, right? This is the y tangent. That's the second derivative of the y. So I plug that in. So it's m times the second derivative, s squared e to the st. Right? And I got to add k times y. So plus k times y, which is just e to the st. Okay, and that's supposed to be equal to 0. Okay, and so at this point in the analysis, what can I always do? Factor out the e to the st. Okay, that's the entire point of assuming e to the st. So I factor it out, and I say e to the st, what's left? I'll have m s squared plus k, right, is equal to 0. So now I'm at a situation where I got 2 things multiplied gives me 0. Okay, and so the possibilities are that either one is 0. So how about e to the st? Is this thing ever 0?
No.
Never. Okay, by the way, this argument applies to every differential equation with constant coefficients that you'll ever solve. Okay? Factor it out, realize that this is never 0, and if that's true, the only possibility is what's in parentheses has to be 0. So that means ms squared plus k is what has to be 0. And so at this point, you want to do a sanity check and realize what you're actually trying to solve for. What am I trying to find here? S. Okay? So M is the mass, K is the spring constant, right? S is what's unknown. So this is it. It's just algebra now at this point, right? It's a quadratic equation for S. Do I need the quadratic formula to solve this quadratic equation? No, right? It's just got an S squared. So this says that MS squared is supposed to be equal to minus K, right? And that says that S squared is supposed to be equal to minus K divided by M. And so apparently S is plus or minus. There's two answers, right? The square root of what?
K over M.
A negative K over M. Square root of a negative number.
Oh, that's impossible.
Is that impossible? So I can write this, right, as what? Plus or minus, do I use an I? J. We like J's because we use these guys for circuits also, right? Plus or minus J times root K divided by M. So how many roots is that? I got 2. So S1 is going to be positive J root K over M. Okay, and S2 is going to be equal to negative J root K over M. Oops, changed my K. Let me make my K the same looking. Like that. Okay, so those are my two values, S1 and S2. Plus J root K over M, minus J root K over M. Okay, so I got two S values. What does that mean then about my transient solution? It's in the recipe. Right? Either one of these S values works, right? There's two answers to the equation. Either one works. So that means the most general solution would be what? Somebody volunteer. I got two S values. Go ahead.
Is it C1 e to the S1 plus C2 e to the S1?
Yeah, so it's the most general result is the combination of both with a constant in front. Right? The reason that's true is because this is the equation I'm solving. If I put a constant in front, I can factor it out. The right-hand side is 0. Right? And if I have two possibilities, the sum of the derivatives is the derivative of the sum. It's just like doing it twice. Right? So I add the two up. It'll still satisfy the equation. Okay? So that's it. All right. So great. So in general, y transient of t is always going to be C1 e to the S1t plus C2 e to the S2t. And so in this case, my S values are imaginary numbers. Interesting. So y transient is going to be C1 e to the S1 j root k over m, e to the j root k over m positive. Okay, times t, right? It's e to the st, so I got a t up there. Okay, and then it's plus c2 e to the minus j root k over mt. Okay, I'm going to write it as this. I'm going to write it as e to the j minus root k over m times time. Okay, so just to be clear, the root k divided by m is all underneath the square root, right? The root k over m is all under the square root. The t is not under the square root. We clear? All right, so two values. I got e to the j theta 1 here, and I got e to the j theta 2. Theta 1 and theta 2 are just opposite signs, right? Okay, great. That's the transient solution. Questions on that? By the way, before we move forward, because you know that's good right there, you're at the transient solution. You know, I'm looking at this for the problem, right? What kind of solution do you think this is? Yeah, I mean, it's oscillating, right? It's a sinusoid. What's e to the j theta look like? Polar form, right? What's the identity? E to the j theta is what? Euler's formula. Who remembers? E to the j theta is the same as complex numbers, hasn't been that long. 4 or 5 weeks.
Cosine theta plus j sine theta.
Yeah, cosine theta plus j sine theta, right? So e to the j theta is sines and cosines. I haven't really made sense out of this yet. It's kind of complicated. I got a couple e to the j thetas. But the point is, the idea that this thing oscillates and the solution's got some imaginary e to the j's, well, that's not that surprising, okay, because it oscillates. All right, but that's just the transient part of the solution. Okay, so we got the transient part. So we're on to step 2. What is step 2 of the recipe? I need a steady state solution. Okay, so steady state solution. All right, and so in general, when I wanted to find the steady state solution, what am I looking at? What's the procedure? Good.
You assume the form of it
You assume a form based on what?
based on the original equation.
Based on the original equation. So this is the original equation, right? Okay, so based on what? What am I looking at to assume the form?
The y of t.
The y of t? The right side, right? The right-hand side? This guy, right? This is the forcing function, f of t. So for this problem, what's the f of t? 0. Okay, this problem is not forced. This is called free vibration. Okay, and so here for this problem, f of t is already equal to 0. Okay, already 0. So if the forcing function is 0, what kind of function can I take its derivative twice, right, multiply by m, add it to itself, put a k on it, and still get 0? Let's think about it. If it's a constant, second derivative is 0, and I'll have k times a constant is 0. So what's the constant have to be? 0. Okay, so if you don't have a forcing function, you can do the exercise you just said. That's fine. Let's assume it's a constant. The constant's 0. If I don't force it, it doesn't move in the steady state. Okay, by the way, the real problem here is not included completely in my model. Right? The model I did basically just said, what are the forces on this thing, right, when it is displaced from 0, right? So here's equilibrium, right, and it said, let's look at it at any time t greater than 0 while it's doing this. Okay, and so what's happening here is when it's at equilibrium, the forces balance, but it's moving at that point, so the spring keeps stretching, right? And now the stretch in the spring is greater than the weight, so it's got acceleration, and it changes direction, right, eventually, and goes up top, and it's back and forth. All right, spring oscillation is because I go between tension and compression relative to the equilibrium spot. Okay, and so it's a restoring force. But if you guys all leave the room and come back in an hour, is this thing still going to be moving? So there's not a lot of drag going on here. Okay, so in reality, every time this thing deforms, the material dissipates a little bit of energy. Okay, the air in the room, this thing is moving through the air, right? The air is a fluid actually, right? And there's pressure in the air, and this mass is moving through the air, and that takes energy. Okay, and so over time, this thing's going to damp out because I'm losing energy. right? And if I have an active damping mechanism in place, like I would try and do in a car suspension, right? You put things like shock absorbers on there. That's what they do. They dissipate the energy, right? If they didn't, you'd be driving down the road and your wheels would be doing this all the time, okay? And that would be a problem because you got springs, right? Big coil springs on the car. So you damp that stuff out and it goes away. So our model doesn't include the damping because, in general, free vibration of a spring with not a whole lot of damping in it seems like it goes on forever. Okay? And so what's going on forever is this transient part of the solution. If I added that extra piece, the damping from the air and everything else, you would see that that dies out over a long period of time. Okay? And if I put a lot of damping, I could damp it out quickly. My model doesn't have that. This is an approximate model here. Okay, and so apparently it's just going to oscillate forever, right? The f of t is 0, so the steady state solution, right, is 0. No forcing function, no steady state. Interesting. So what's step 3? I got a transient, I got a steady state. Total solution. All right, so how do I get the total solution? I add the transient and steady state, right? So what I want is y of t is equal to the sum y transient of t plus y steady state of t. So here's the thing. Whenever the right-hand side is already 0 at the starting point, the total solution and the transient solution are the same thing. Okay, I'm not adding any steady state because it's 0. So apparently then, y of t is just what we already have up there. It's c1 e to the j root k over m t plus c2 e to the j minus root k over m t. Okay, that is the total solution. By the way, what's unknown still at this point? Yeah, I don't know the C1 and C2 yet, and that's the next step. But before I get to that step, wouldn't it be nice if we could get this in a, in a form that made sense to us in terms of this oscillation here, right, as opposed to a form that looks like an exponential function. All right, so why don't we go ahead and apply that Euler formula, okay, and see if we can see how this thing turns into sines and cosines. Okay, so if you guys recall, Euler, right, the Euler's formula, which is e to the j theta is what?
Cosine of theta plus j sine theta.
Yeah, it's a cosine theta, right, plus j times a sine of theta. That is the Euler formula. Okay, and so the thing is, each one of these terms is a constant times an e to the j theta. The theta is whatever's next to the j, right? So let's expand this guy out. All right, if this is true, then y of t, I'm going to have c1 e to the j theta. So it's the cosine theta. Okay, so e to the j theta. So I'll write this as the cosine of theta root k over mt, okay, plus j times the sine of theta root k over mt. That's the first term. Plus, I'll write the second term, c2. So what's the difference between these two thetas here? Theta in the first term, theta in the second term. It's just a negative sign, right? So I'll write it out so we're clear. This is the cosine of negative root k over mt, right? Plus j times the sine of negative root k over mt. Okay, and so I got to think about, what's the difference between a positive and a negative angle. Okay, I can come over here and just remember my trig a little bit here. All right, so if this is positive theta, okay, and this is negative theta, okay, then you tell me, when I take a cosine of a negative theta, how does that compare to the cosine of the positive theta? Looks to be the same, right? Cosine is this part, right? The horizontal. How about the sine? The sine of the negative theta is really the opposite, right? It's the negative of the sine of the positive theta. Okay, and you could convince yourself this is true no matter what quadrant this angle's in, right? So if I was over here, this would be positive theta. Negative theta would be all the way around here, okay? And so it'd be the same argument. So no matter what quadrant I'm in, I can always say that that is true. So I can actually then simplify this guy a little bit. Okay, and what's this going to look like?
237 of t times kilograms squared.
So is it going to be 2 times it? So here's the thing. Let me be clear. This whole first term, cosine of minus root k over mt, this is the same as the cosine of positive root k over mt. Right? In other words, the negative sign doesn't matter. This guy over here, this term, right, is going to be what? J times what? The negative comes out front, right? So this is really times a negative sine of root k over mt. Okay? So, right, that's what I'll have here. So in this parentheses, I will have C2 multiplied by all of this. So let's take a look at the algebra here. So I got a cosine root k over mt here times C1. I got a cosine root k over mt here times C2. How can I simplify that?
Pull out the cosine.
Yeah, the cosine term is in each one, right? So it multiplies by C1 plus it multiplies by C2. So can I write the cosine terms as y of t is the sum C1 plus C2 times the cosine root k over m times time, right? Here's the C1 cosine. Here's the plus C2 times the same positive cosine. How about the sine terms? I got a sine root k over mt here. I also have a sine root k over mt here, right? But this one's got a minus. They're both multiplied by j, so it's a c1j times the sine. And it's a negative c2j times the sine. Right? So how could I write that? Yeah, c1 minus c2. Right, so plus C1 minus C2, I still have a J also, right? C1 minus C2 times J times the sine root K over M T. All right, now here's a little trick that you might like. Okay, and let me motivate this trick as follows. Are you ready? Here's the solution, okay? Is y of t real or imaginary?
Real.
It's real, right? I'm looking at it, okay? So clearly the real displacement is not imaginary, okay? Good. So what if I said this guy, C1 plus C2, is C3, okay? Because I don't know what C1 and C2 are yet. They're constants to be determined, right? If I take 2 unknown constants and add them up, I just get a third unknown constant, right? How about this? What if I take C1 minus C2 and multiply it by J and call that C4. Does that seem shady? So now y of t would be C3 cosine root k over mt plus C4 times the sine root k over mt. No more J. Raise your hand if that bothers you. We only got one non-liar in the classroom. Okay, couple. All right, seriously, this doesn't bother you guys? Where'd the J go? Is it in the C4? What I said was, what if C1 plus C2 was C3? And what if C1 minus C2 multiplied by J was C4? Right? That's what I said. Does it bother you? Well, I mean, so why would I say that? Well, it's back to this question again.
Since it can be imaginary.
Yeah, I mean, is the displacement real or imaginary? It's real, okay? So that's a physical statement that says, here's the key, C3 and C4 had better be real. What about C1 and C2? Yeah, C3 is the sum of C1 plus C2. C4 is the difference between C1 and C2 multiplied by J. If C1 and C2 were real, then when I subtracted them, I would get 0. I'd get a real number, and when I multiplied it by J, would it be real anymore? No. So if C3 and C4 are real, C1 and C2 can't be real. That shouldn't really bother me, right? Because I said my unknown constants here were written in terms of complex exponentials. I got j's in the exponent. No one said the constants had to be real numbers. Okay, they're just unknown constants. Okay, but what I am saying is that y of t needs to have real numbers, so C3 and C4 have to be real. So here's a real one for the truly astute student. If C1 and C2 are complex numbers, how can I take two complex numbers and add them together and get a real number? And more importantly, equally importantly, how can I subtract two complex numbers, not different ones, the same ones as these? How can I subtract two complex numbers, multiply by J, and get a real number? Right? Because C4 has to be real.
J squared is -1, right?
That's true.
So would they both have to be imaginary to begin with, the C1 and C2 values?
Well, if they're both imaginary to begin with, then if I add them together, can I get real? You're barking up, you're getting warmer, okay? Barking up a close tree.
Wouldn't you want to get a 0 for C1 plus C2? Is that way you get rid of the J?
Well, so if I got 0 for these, then that would mean I couldn't have the cosine term here, right? I mean, that could be part of the solution. It depends on what the initial conditions are, right? Let me ask you this. What if C1 is equal to A plus J times B? And what if C2 was A minus J times B?
So the imaginary can cancel out.
What happens when you add them up?
J, B is gone.
When I add them up, I get 2A, right? What happens when I subtract them? If I subtract them, The A's are gone. I get 2JB. 2JB multiplied by J. Yeah. What are C1 and C2? Say what? Conjugates. Right? That's what they have to be. Okay, so this is kind of it's an aside. And by the way, you don't have to go through all this whenever you solve one of these, so I'll make that clear in a minute. Okay, but, you know, if C3 and C4 are real, okay, in other words, C1 plus C2 gives me a real number, C1 minus C2J gives me another real number, then essentially C1 and C2 must, okay, be complex conjugates. Okay, that's a statement, right? So if C3 and C4 are real, then C1 and C2 have to be complex conjugates. It's the only way it works out. Okay, now, does that restrict the problem in any way? Let me ask you this. At this point, how many unknown constants do I have? 2. And in this view right here, those two numbers are C1 and C2, right?
Yeah.
If I constrain C1 and C2 to be written like this, how many parameters do I need to specify C1? A plus J times B. I need 2. I need an A and I need a B, right? Do I need any more for C2? No, it's still A and B, right? So the point is, it's still 2 unknowns. A and B are still unknown, right? Over here, C1 and C2 are still unknown. This is a second order differential equation, right? So I'll have how many initial conditions? 2. Second order will need 2 to specify 2 unknowns, right? So the point is, the fact that I know that C1 and C2 have to be complex conjugates is not me constraining the problem in any way. It's just a statement that the solution to this piece of physics is a real number, right? And that's perfectly acceptable because the unknowns are really the A and B, right? That make up the 2 halves of the complex conjugate, C1 and C2. Okay, it's still 2 unknowns that I specify with initial conditions. So why not instead write it like this, C3, C4, right? Where I know off the bat, C3 and C4, they're unknown at this point still, but they're definitely real numbers. And then I'm done. Okay, so the point is this step of saying, hey, add these and give me C3, subtract them, multiply by J, give me C4, that's not cheating. Okay? It's recognizing that that has to be the case, and you can see what the implications are on the math. Right? It has to be the case, but the implications are that those C's over there are complex numbers. I don't want to deal with complex C's anyway. Why would I want to deal with complex constants? Okay, let's just deal with real ones. You guys with me? So here's the thing. Whenever I get a steady state solution, a transient solution that has S1 and S2 that are J's, okay, then always I can just jump straight to this right here, right? So it's e to the j theta. The theta is S1t, right? S2t. It's just cosine theta and sine theta. Okay, so when you do that step of solving for the s's, if you get real numbers, the answer is a decaying exponential, right? Or a growing exponential. Okay, if you get imaginary numbers, the answer is sines and cosines. You just go straight to that step. Okay, so we'll see that as we move on. We'll solve more problems that have sines and cosines. Okay, so this guy right here is the general solution, right? Right here, C3 and C4. All right, so what's next? Got transient solution, got the steady state solution, got the total solution, except for the constant C3 and C4. So I need to apply initial conditions. Okay, so in general, when we give you a starting point for a diffie-q, we will give you the equation and the initial conditions. Okay, this one we're kind of walking through the physics as we go. So let's see if we can specify what these guys are. All right, so the very last step is to solve for these initial conditions. So you guys help me out. The unknown function's the y of t, right, which is the position itself as a function of time. Okay, and I'm going to need how many conditions? Two. I got two unknown constants, C3, C4. All right, so right now this is the statics problem. This is not the differential equation problem. Okay, and then we give it an initial displacement, right? And as soon as you say go, I let it go. So my initial condition is right now. All right, so who wants to help me out? What are my two initial conditions?
Is your maximum?
Say that again?
Is it like your maximum and minimum displacement?
My max and I like that. So my initial condition, right, what he's saying is my maximum displacement. Right, so recognizing already that the biggest displacement I'm ever going to get is the initial condition. Okay, but the initial condition is basically just an initial displacement. See how it comes right back to where I let it go? Right, and so that's the way it works. Right, so an initial displacement, absolutely. So let's call that y of 0 equals whatever, 1 inch, 2 inch, whatever. Let's just put an amplitude on it since you said it was the max. I'm going to call it A. Okay, so this is the initial displacement. Okay, so I got one condition, the initial displacement, that is known. Okay, so this A is not an undetermined A, it is an actual magnitude. 1 inch, 2 inches, whatever that initial displacement is. So I need one more condition. All right, here I am. Time equals 0. Initial displacement is A. What else do I know at time equals 0? The weight. So is the weight, is the mass an initial condition? Okay, so just to be clear on this, the mass is in the governing equation, right? Because the governing equation is sum of the forces equals ma, mass times acceleration. Right, so the mass is built in to the equation that includes acceleration. That's not an initial condition, that's a condition that holds for all time. Okay, so what I would get from that, that's this. This is sum of the forces equals ma right here. Okay, and so I've already got that taken into account. Any other ideas?
The initial acceleration?
Initial acceleration, well here again. This is an equation for the acceleration, which is true at all times. So this is already also true at time t equals 0. Right? In other words, the acceleration. Anything related to the acceleration is included in the governing equation because that's what the governing equation is. It's the statement, sum of the forces is mass times acceleration. Okay? Getting there. Yeah. Velocity. All right, so look, in general for dynamics, if you're taking care of position and the governing equation has acceleration, there's only one thing left that we haven't talked about, right? And that's velocity. So in dynamics in general, second order problem, I need to know where it starts and I need to know how fast it's moving. So you tell me, how fast is it moving? 0. Okay. So I initially displace it. It has no initial velocity. But as soon as I let go of my fingers, the forces are not balanced, right? So again, back to this issue. The initial acceleration is not 0. Right? And I can see what the initial acceleration is. Right? The initial displacement is A. So the stretch in the force in the spring is K times A. The initial acceleration is K times A divided by M. Negative. Okay, so it's built into the governing equation. So at the very beginning, I automatically have initial acceleration, but it's not an extra condition. It's built into the governing equation. Okay, the extra condition is knowing whether or not it's moving at the beginning. right? Because I could have a different problem, right? Like for example, this one, where I just drop this, and now it free falls, right? So if I start the clock here, it was already moving when it got to that point, okay? And it's a different problem than the one where this is the initial condition. It's got a displacement, but it's not moving. And as soon as I start the clock, the forces are unbalanced because the spring is stretched, so I let go, and bam, it starts to go, okay? So initial displacement, no initial velocity. How do I write that down with math here? V of 0 equals 0. So my unknown here is what? Y. So how do I write down V in terms of Y? It's the first derivative, right? So Y dot of 0 equals 0. This is the initial velocity. Okay, so in general, guys, for dynamics problems, you have initial conditions on position and velocity. The governing equation takes care of any initial condition on acceleration, which is basically a statement that the forces are not balanced. Okay, built in here. Great, so I got two conditions. What am I trying to solve for? Do I want C1 and C2? I could solve for C1 and C2, but they'd be complex numbers, okay, and that would be annoying to me. All right, so I'd rather just solve for C3 and C4, and those had better be what kind of numbers? Real numbers. Okay, so we'll solve for those. All right, so how do you apply an initial condition? Suggestions for this? Plug it in, right? So easiest to start with, the easiest one to do. So I got y of t. Why not apply the initial condition on y and see if I can solve for one of these constants? Okay, so the first one, y of 0, right, is equal to what? Well, we take y of t and we put in 0. So it's c3 times the cosine of 0, right, plus c4 times the sine of 0. Okay, and that is supposed to add up to give me what? A. Okay, so it doesn't add up to 0. Now, what's the sine of 0? So this term is gone. So the conclusion from the first initial condition, that's this guy right here, okay, is the cosine of 0 is how much? 1. So apparently the C3 is equal to A, right? So at this point, not a bad idea to write down what you know. So this means y of t is, okay, C3, we found it. It's A times the cosine root k over m t. I know the A. Plus, it's now C4 times the sine root k over m t. See, so I applied one initial condition, and I got one of the constants. How will I get the other constant? All right, I need to apply the next initial condition. Yeah, so here's the key thing, right? It's not evaluate y at 0 and then take the derivative. It's take the derivative and then evaluate that at 0. Okay? It's actually a pretty common mistake students make, right? If I evaluate a function at a certain time, do I get a function anymore? No, I get a number, right? And if I take the derivative of that number, I get 0. Okay, so the order of this matters, right? This is evaluate the derivative at time t equals 0. So you need the derivative. So the next step is I need y dot of t. Now, I'm going to write this all out here so I don't lose anybody. But in general, when you start solving these problems, not a bad idea to be able to do this kind of in one step, like take the derivative, plug in 0, and just write the answer. Okay, I'm going to put the intermediate result just to be clear. What's the derivative of the cosine root k over mt? Derivative of this term is what? I get a negative sign. What happens to the a here? Stays out front. What about the root k over m? comes out front, right? Again, you guys understand all of this is the argument of the cosine function, right? It's all inside the cosine. T is the last argument. Okay? And so the a stays out front, right? And what I get is a negative root k over m, right, times the sine root k over mt. That's the derivative of the first term. Okay? And then I got the second term. What's the derivative of the sine? Cosine root k over m comes out front, so I'll have c4 root k over m times the cosine root k over m t. That is now y dot at any time t. So now I want to apply the condition y dot evaluated at 0. Now that I have the derivative, I can plug 0. So what's the first term?
0.
Yeah, this is minus a root k over m, right, times the sine of 0. Okay, great. So that first term is going to be gone. Second term, I'll have c4 root k over m times the cosine of 0. And when I evaluate y dot at 0, what am I supposed to get? 0. That's the condition, right? Y dot evaluated at 0, set it equal to 0. So take a look at that. What's the conclusion? Yeah, I'll write out one more intermediate step, right? But essentially what you get here is the first term, sine of 0 is 0. So you get 0 plus cosine of 0 is 1, right? So it's c4 times root k over m. And that's supposed to be equal to 0. So therefore c4 is what?
0.
C4 has to be 0. Question?
There wasn't a tendon sheet passed around, right?
You know what? No, because it's sitting right here. There is now. Thank you. Okay, so C4 is 0. So I got C3. I got C4. Sounds like I'm done. So what's the solution look like? Y of t is equal to a cosine root k over m times t. Okay, so go back to the problem. Okay, right? Here's the problem. Initial displacement. Okay, and let it go. There's the answer. Cosine function. By the way, what's the frequency of oscillation? Let's look at all the things here. What is A? What does A represent? Yeah, this is the amplitude, right? We're back to sinusoids. By the way, you wonder why we treat sinusoids as a whole separate topic in this class, right? They are common solutions to engineering systems, right? So we got to understand what these things do. A is the amplitude, okay? What is the angular frequency? That's the omega, right? Okay, but in this case, we're going to call this omega n, right? Omega sub n. N stands for natural frequency. Natural frequency is a term that means if I just perturb something and let it go on its own. Here it is. I perturb it, I let it go. It will want to oscillate at a certain frequency all by itself. Okay, I'm not forcing it. There's no forcing here. I'm just letting it oscillate. Free vibration. Whatever that frequency is the natural frequency of the system. In this case, according to this, is what? Is it k over m? It is the square root of k over m. Okay, this is called the natural frequency, okay, of the oscillation. Okay, and so back to the question, when I put the second mass on here, where'd the second mass go? Right? It went, how much slower did it go? Did it go twice as slow? 30% slower, right? It did 7 cycles instead, okay, of 10 cycles. So, can anybody give me an explanation for that based on the answer here? how would you explore that idea based on the frequency of oscillation here?
What was the question?
The question is, right, the whole reason we solved this was because we observed one thing with one mass, right, and then we put two masses on and observed something we didn't expect, right, which was it didn't go half as fast. It went 70% as fast. You know, if I went through all this trouble to solve the differential equation, you'd think I could have an answer for that.
Because the mass is part of the function, it's inside,
Okay.
cosine underneath k and the rest.
So how does that explain the 7 instead of the 10?
Mathematically,
Uh-huh.
because it's only, it's not gonna, since it's twice as much, it's gonna divide the k by that much more. And since it's underneath the calculator.
Okay, because it's underneath the square root, right? So if m goes to 2m, okay, then omega n goes to what? It's the square root of k divided by 2m, right? Double the mass, that's the new answer, okay? And isn't this the same thing as 1 over the square root of 2 times the original root k over m? Right? Which is 1 over root 2 times the original frequency. What's 1 over root 2? 0.707, right? 0.7 omega n. Okay, so instead of 10 cycles, I get how many? 7. All right, there you go, right? Accurate differential equation. By the way, the frequency of a damped system is not the same as the natural frequency, right? And so the real answer to this problem is not exactly that number because there is damping here. But for a spring like the one I have, and this thing moving through the air, the damping is really light, right? Like if you come back in an hour, this won't be moving. But if you come back in like 3 minutes, you know, my arm will be tired and it'll still be doing this. Okay, and so it's really light damping. But if you have heavy damping, it actually changes the frequency, and that's a result that involves a little bit more complicated equation. Okay, but you can predict that with the same kind of math. All right, very good. Questions? So this isn't really the fun part yet. This is the free vibration. The fun part is force vibration. Yes?
What happens if you take root k over m in the equation right here? You have root k over m, then you say w n is equal to 1 over root 2.
Yeah, so what I said is if the frequency is root k over m, yeah, if the mass is doubled, that means m gets replaced with 2m. So you take the original root k over m and you replace the m with 2m, but I can take the 2 out, and now I have the original frequency, right? So the effect of doubling the mass, right? This is, by the way, the reason we solve the problems with letters in them, right? So we can predict this stuff. If it was just a number, I wouldn't have the insight, okay? But because it's a parameter, now I can double the parameter and see what happens. Okay, so same idea. What if I make the spring twice as stiff? K would be 2k. Would the frequency increase or decrease? Increase, right? K is in the numerator. By how much? Root 2, which is? Is it? Yeah, it's 40%, right? 1.414. 41% faster if I double the stiffness. Okay? 30% slower if I double the mass. Right? Okay, good. Very good. So, by the way, you know, in general, this thing right here, this is a general result. The frequency increases with stiffness, right? So if I increase the K, it vibrates faster, okay? By the way, you know, that right there, that noise, that's vibration in the air. That's what noise is, right? Acoustic waves. Listen to this one. All right, so here's my fist, and here's the weight. Which one of those is higher pitched? The weight. What's stiffer? Am I the man of steel here? Or is this a steel weight? Right? Okay, so that's it, right? The stiffness of the material. It's not just the material, right? But the stiffness of my entire fist relative to that, okay? And that impact. So increasing stiffness makes it go up. Higher frequency is higher pitch. And this thing also decreases with mass. Okay, and that's part of the equation too, right? So if I have more mass, the frequency goes down. This is a general result for vibration of mechanical systems in general. All right, so more interesting problem. What if I take the same thing, okay? And we'll be able to use some of what we already have here, okay? But what if now I add a force to this thing? Okay, so let's suppose now that I add a forcing function, I'm going to call it small f of t, equal to capital F times the cosine omega t. Okay. What changes with the free body diagram? Does everything change? So now I've got this on here now, right? F cosine omega t. So if I redo this entire equation, I displace it from equilibrium, do I still have gravity? Yep. Do I still have a spring force?
Yes.
Yep. So I got one extra term in the equation, right? What's the term? It's just this, right? So immediately, I could redo the force balance, but all this does, the reason I even called it this, it just ends up on the other side. So I end up now with an equation that looks like m y double dot plus k y of t, and instead of nothing on the right side, I get this guy, f cosine omega t. Okay. So, interesting. Plus whatever my initial conditions are, right? I could start with an initial displacement. In this case, if I'm going to apply a forcing function, I could start with no initial displacement if I want, right? Because at time t equals 0, I could just start ramping up a force. Or in this case, if it's a cosine function, at t equals 0, the cosine is how much? It's 1, right? So that would be like a suddenly applied force, right? And then it's going to be a cosine the whole way through, right? So I'm forcing the thing, but I'm following it with the force the entire time. Okay, so this is called forced vibration now. Okay, let's redo the whole problem. What's the answer now? So we'll pick up the clip a little here since we're running a little low on time. What's the transient solution? I'm sorry, what was that? Same, right? Because don't I just set the right-hand side equal to 0, right? And if I do that, don't I have the same problem I just already solved? Right? So I'm just back there again. So I could go through this whole e to the st business if I want to do that, and let me be perfectly clear. On a final exam, we want you to go through the whole business, whether you see a problem that looks similar to something or not. We want to see the steps. But I'm not going to repeat it here in lecture. I'm going to realize that the transient solution, y transient of t, is going to be c3 times a cosine root k over m t plus a c4 times a sine root k over m t. Okay? So this is the same. Right? And in fact, I'll write that here just to be clear. This is the same as we had before. Okay? And so we can conclude that. So the difference between a forced vibration problem, okay, and a non-forced one, it's got nothing to do with this natural frequency. The natural frequency is this root k over m. Note that this guy, the applied force, this omega, is a problem parameter. Be whatever frequency I want, right? Not necessarily the frequency that it would go on its own. Okay? Different frequency. So step 2. I need to do what? I need the steady state. So, in this case, I look at the original equation, right? Which is my double dot plus ky of t is capital F cosine omega t. And I have to understand that the right-hand side now is now my forcing function f of t, right? No longer 0. So, if that's true, how do I find a steady state solution? According to the recipe. Go ahead.
You assume that the cosine of omega t is the same as a sine of omega t plus b sine, or b cosine of omega t.
Yeah, so I want to assume, again, according to the sheet here, look, I'm trying to find a function, y steady state, where when I take its derivatives, add it to itself, I get a cosine function. Well, it's going to have to be a sines or cosines, right? It's the only way it's going to work. So what I do now is I assume a form of the solution. Right, so I will assume a solution that looks like y steady state of t is a times the sine. Is that right? I'll stick with the notes to make sure we're clear. Yeah, a sine plus b cosine plus b times the cosine omega t. So here's the key point. Whatever the omega is that I'm forcing it with, okay, is the same frequency that it will oscillate at in the steady state. If the free vibration damps out over time and it's gone, then the output is whatever the input is. Okay, if I'm doing this, this is how it's moving. So what am I trying to find there? A and B, right? The omega is given, part of the problem statement. Forcing frequency, I need A and B. So how am I going to find the A and B? Do I do initial conditions to find this A and B? Because keep in mind, I also need to find what? I need the C3 and C4, right? Initial conditions will get those, but I don't want to do that until the very end, okay? Because the initial conditions apply to the whole solution, not just part of the solution. Okay, other big mistakes students make in DiffyQ solving, right? You get a little antsy, you want to knock out the initial conditions early, right? The initial conditions are the real conditions on the whole problem. You need the whole solution to apply the real initial conditions, right? So for this part of the solution, the steady state, how can I find an A and B that, when I substitute it in, gives me this on the right? Set it equal. So I'm trying to find what? A and B. And the A and B have to be such that this equation's satisfied, right? So what should I do with that assumed solution? I need to plug it in. All right? Let's plug it in and see what I can conclude about A and B. Now when I plug that in, I need to plug the whole y of t here. What do I need to plug here? I need a second derivative. Can we do this in one step? What's y double dot steady state? Can we do this in one line? You just do the derivative twice, right? So the first derivative,
Negative a omega sine omega t squared. A omega squared.
so derivative of the sine is the cosine, right? And the omega comes out. Take the derivative again. Derivative of the cosine is back to the sine with a negative, and another omega comes out. So don't I get minus a omega squared times what? Back what I started with. Sine omega t, right? Plus two derivatives of the cosine. First derivative gives me a sine, negative omega out front, Derivative again, back to cosine, no extra negative, the negative's still there. Another omega comes out, so I get minus b omega squared cosine omega t. Okay, if you guys don't like that in one line, feel free to just go ahead and take the derivative twice, okay, in 2 lines. All right, so now I got to plug this whole thing in to this equation. I'm going to ramp over down here so I got the length to do it. So it's my double dot. M, here's y double dot, minus a omega squared sine omega t minus b omega squared cosine omega t. Okay? This is my double dot plus k times y plus k times y, which is the original, a sine omega t plus b cosine omega t. So just to be clear, I got my double dot plugged in. I got plus k times y plugged in. And this has to be equal to f cosine omega t. How many equations do I have here? It's a pretty straightforward question. How many equations do I have here? 1. How many unknowns do I have? 2. Okay, generally that's a problem, right? 1 equation, 2 unknowns. But like, you know, in statics, sum of the forces equals 0. Well, that's 1 equation, right? But I got x direction, y direction, and 3 dimensions. I got the z direction, so I've got i's, j's, and k's. I can get 3 equations out of 1 vector equation. Right, remember when we did sinusoids? Can I write a sine and a cosine as a single sine or cosine with a phase shift in it? Okay, it's the same exact math that we need to do here. Right? If I'm going to take some stuff times a sine omega t and some stuff times a cosine omega t, and I'm going to add it up and get an f times a cosine omega t, can't I group the sine and cosine terms and deduce what these coefficients have to be? Right? It's just like equating i's and j's. It's just exactly like equating the sines and cosines when we did sinusoids. Exact same math. You guys with me? So let's manipulate this. I want to get this so I have like terms that I can look at. So again, at this point, the more algebraically adept that you can be, the less writing you have to do. Okay? That being said, you know, only do as much algebra in 1 step as you personally feel comfortable with. Okay? Here, I need to preserve ink when I can. Okay? So if I look at the sine omega t terms, okay? What? In front of a sine omega t, what do I have? I got a in front of both of them. I also have a k with this term and a minus m omega squared with this term. Right? So I'm going to write this. I got an a with both terms. I got a k minus m omega squared. Right? Here's the k. Here's the minus m omega squared. All of that multiplies the sine omega t, right? When you try and do this in 1 line, just go back a step and check, right? Here's my terms. A k sine omega t, that's this guy, minus a m omega squared sine omega t, that's this guy. I don't have any more sines. I'm done. You guys with me? Yes? Okay. Plus, I got cosine terms. Here's a cosine omega t here. Here's a cosine omega t there. They both have a b, right? So I'll put a b. And what else do they have? This one's multiplied by k. This one's multiplied by the same thing, minus m omega squared. So don't I have k minus m omega squared cosine omega t? And isn't this all supposed to be equal to f times the cosine omega t? So take a look at the two sides of the equations there. On the left side, right, I got something times a sine omega t plus something times a cosine omega t. And on the right, that equals f times a cosine omega t. So I would argue that I could look at the sine and cosine as functions that one of them is 1 when the other one's 0. Right? So I have to separately be able to group these terms. So what can you say about the coefficient of the sine function? What do you guys think? Something times sine plus something times cosine equals something times cosine. What's the part in front of the sine have to be equal to? 0. Right? It's the same exact math, guys, when we did sinusoid, right? So isn't it true then that a times k minus m omega squared has to be equal to 0? Okay, and if I look at the cosines, right, matching the left side to the right side, what can you say? That b times k minus m omega squared has to be equal to what? F. Okay. So, this will work out, right? Top equation, what am I trying to find here, by the way? I'm trying to find m. Okay. A. I want the a and b. This one implies what? A is what? A is 0. This is true if, right, this guy's not 0, right? K minus m omega squared is not equal to 0. Okay, I'm going to assume that that's not 0. Why would it be safe to assume that's not 0 at this point? Well, the second equation's got the same thing. So if it's 0 in both terms, is this thing doing anything? No. So I'm not interested in that particular case. So there could be one case, right, when that's true. Okay, and all right, so then if that's true, then that would mean b is equal to what? Yeah, f divided by k minus m omega squared. Okay, that's it. Great. So let me cap us at a neat place, and we'll have to finish up next time. Okay, so this means that y steady state of t is going to be what? A is 0, right? So it's a cosine. It's b cosine. F divided by k minus m omega squared, okay, that whole guy, times the cosine omega t. So here's where we're going to pick up. We got a steady state. We got a transient, right? What's left to do? Total solution, initial conditions, and see what happens. Okay? So we'll finish that up on